Hello. Okay, welcome to week two of the problem solving sessions for the course Introduction to Wireless and Cellular Communications. I'm your tutor Sachin from the EC department in the Indian Institute of Science. First question. Consider a scenario where a relay node is used for extending the coverage of a base station. The relay node is transmitting with a power of 10 milliwatts, and the user measures the received signal power as minus 90 dB watts. If the carrier frequency is 900 megahertz and considering the free space path loss model, what is the distance between the relay node and the user? Power transmitted is 10 milliwatts. If we write that in dB, it is 10 log of 10 milliwatts is 10 power minus 2 watts. It is minus 20 dB watts. He received is minus 90 dB watts. Frequency of the carrier is 900 megahertz, from which we can find out lambda, which is C over F, which is 3 into 10 power 8 divided by 9 into 10 power 8, which is 1 over 3 meters. Now we have to use the free space path loss model, which says that the P received in dB watts is P transmitted in dB watts. In the lecture video, they didn't really write it in terms of dB watts, but this minus 20 log 10 4 pi d over lambda. Lecture it was, yes, in watts you just take log on both sides and multiply it by 10. This means P received, which is 90 minus 90 is equal to minus 20 log 4 pi d divided by 1 over 3. So 20 log 12 pi d is equal to 70 log of 12 pi d is 7 over 2. So d is 10 power 7 over 2 divided by 12 pi. If you put that in a calculator, you will get d, and d here is in meters. So I'll leave the calculation part to you. You can verify that you get 83.8 meters. Derivation for this formula was done in class. Question number 2. Consider a base station whose transmitting antenna gain is 10 dBi. This is 10 dB isotropic. A 1 watt signal is sent to an ideal amplifier whose gain is 10 dB. Then the amplified output is connected to the antenna by a cable, and as it was taught in class, the cable can have a loss uh, that can introduce a loss. So the cable also has, this question is, the cable has a loss of 6 dB. What is the effective isotropic radiated power? EIRP. So since everything here is in dB, we just need to add things up. So the effective isotropic radiated power is, first, how much is your signal power, and then how much is that amplified by. So you add the amplifier gain, It was not in dB, you would just multiply. Then subtract the cable loss. If it's not in dB, you divide. And then that is transmitted via an antenna, which itself has a gain. Signal power, it's transmitting 1 watt, so it's 10 log 1 to base 10, which is actually 0. Plus amplifier gain was 10 dB. Cable loss was 6 dB. And then antenna gain was 10 dB, 10 dBi. So first term is 0. 10 minus 6 plus 10 is 14. 14 dB watts. Question number 3. You have a 5 gigahertz WLAN link. A 5 gigahertz WLAN link has a receiver bandwidth of 20 megahertz. The receiver has a noise figure of 6 dB. If QPSK modulation is used, what is the receiver sensitivity required to achieve a bit error rate of 10 power minus 5? So you can find a cube function calculator. Of course, you could just search it online. This is what is given in this course at the following address. You can find a Q function calculator, inverse Q function also is there. Slash You can find it easily in that link. Okay, now they have given it's QPSK modulation. So what QPSK, the bit error rate is in terms of the Q function, Q into 2 root of EB by N naught, which is given to be 10 power minus 5. You do the inverse Q function and you'll find out. You'll find out the inverse Q of that is 4.26 something something. I'll just take it as 4.26, and then you can find out the EB by N naught from that. You do the calculation, it will turn out to be 9.07. And we know for QPSK, SNR is PS by PN, which is 2 times EB by N naught. So EB by N naught was PS by PN into TB by TS. So symbol bit duration by symbol duration. Since QPSK has 2 bits per symbol, symbol duration is twice the bit duration, so we get effect of half. Here it's the other way around, so PS by PN is twice EB by N. This is 18 point something. This will be 12.59 in dB. I'll leave the calculation parts to you. Now we have that noise power is the thermal noise, ambient noise, whatever you call it. It's just 10 log of kTB. Actually, you can write it as 10 log of kTBF. F is a noise figure. F is a noise factor. And then since it's logarithmic, you can split this up. kTB plus 10 log F. So 10 log F is the noise figure. 10 log kTB is your thermal or ambient noise. Just plug in the values of K, TB, F, everything is. So noise figure was 6 dB. Given is 10 log F is 6 dB, and temperature they haven't really given. You can just take the room temperature. -25. I'm not sure what exactly. Yeah, we'll just assume it's room temperature. And then bandwidth is given as 20 megahertz. So you plug in all the values, you will get the noise power to be minus 124.82 dB watts. Now you have the noise power and the SNR. So your receiver sensitivity is PS, which is PN times SNR, but in dB it's SNR. dB plus PN dB watts, which is 12.59 minus 124.82 minus 82 something, 82.23 dBm. So from dB, if you want to go to dBm, you just add 30. So this is actually minus 112.23 dB watts. Sometimes the option will be in terms of dB watts, sometimes in dBm. So if you want to go from dB watts to dBm, you add 30. If you want to go from dBm to dB watts, subtract 30. Yeah. Q, you see this link I have given. Hello, I did not understand your question. Ah, 10 power minus 5. You Yes, you have to do inverse Q function. So square root of 2 EB by N naught is Q inverse of 10 power minus 5, 0.00001. And then click on inverse Q function. Yes, then it will give you 4.26. If it is a multiple choice question, it will be there in the options. The options will be in dBm or dB. If it's not multiple choice, you can write any of them. It's okay. If they haven't asked you to write in any particular units, then you can write in whatever units you want. You can even convert to milliwatts or watts and write that also. If they haven't asked, they specified write in dBm or dB, you have to write in that. Otherwise, you don't even have to write in dB. Okay. So question 4 is a continuation of the previous one. In continuation to the above question, assuming the transmit transmit and receive antenna have 2 dBi gain each, what is the range achieved for 100 milliwatt transmit power Using a link margin of 20 dB, use free space path model. So we have calculated receiver sensitivity in the previous question, which is minus 82.23 dBm. Now we transmit with for PT, we have a gain from the transmitting antenna, then we have a gain from the receiving antenna, we have a loss from the path loss, then we have to give some margin, and this power must be greater than or equal to receiver sensitivity if your receiver must work properly. If you want BER to be 10 power minus 5. That means the transmitted power, which was given in the previous question, which was sorry, it's here, it's in this question, it's 100 milliwatts. So transmit power is 100 milliwatts in dB, that will be in dBm, that will be 20 dBm. So one thing where you have to note while adding these quantities is that if the quantity is dB or dBi, which is dimensionless, you can add it to any other um, unit. Like you can add it to dB watts or dBm, doesn't matter. But you can't add something that is in dBm and something that is in dB watts. Doesn't really make sense. You have to be careful. You can add all quantities in dBm or all quantities in dB watts. dB doesn't matter. You can add dB. dB is just a scaling factor. But you can't, when it's in dB, it means it's a dimensionless quantity. But when it's in dBm, it means dB when it's with reference to a milliwatt. When you write dB watts, it's with reference to a watt. So you can't add dBm and dBw. So since receiver sensitivity, we had it in terms of dBm, we'll just keep it that way and write PT also in dBm. So that's 10 log 100. Log 100 is 2, so it's 20 dBm. Both the transmitter and receiver gains were 2 dB. Path loss from the free space path loss model, it's if you write it in dB, 20 log 45D by lambda, and then we have to give a noise margin of 20 dB, and this power must be equal to your receiver sensitivity. They have given 5 gigahertz wireless LAN, so frequency is 5 gigahertz. You can find the wavelength p into 10 power 8 by pi into 10 power 9, 3 over 50, 0.06. You substitute that. The rest of it is just mathematical manipulation. And here the unknown quantity is D. You know everything else. So D will turn out to be 97.82 meters. So what this means is that In the above situation, if you want receiver sensitivity to be minus 82.23 dBm, you're transmitting at 100 milliwatts. You also want to give a link margin, an error margin for your outage, which is 20 dB, and your antennas are giving you extra gain, 2 dB each. Then you can transmit up to 97.82 meters. You can't transmit further than that. If you do, the power that is being delivered to the receiver will be less than your receiver sensitivity. And then if that happens, your receiver won't can't guarantee you a BAR of 10 power minus 5. Question 5. Ah, this particular question, exactly this question is there in your assignment. Let me see. Let me check. Which question is it? Question 4. Hmm. Yeah, the receiver sensitivity is also different, right? It is 82. I think what has happened is they have copied the question without changing the parameters, but the options they have changed. No, there's no reason. Whichever is convenient, you can do. But then you'll have to. Finally, the answer has to be in whatever units are there in the options. No, then you'll have to put P transmitted and receiver sensitivity both in dB watts. Then it shouldn't change. Both should be in dB watts or dBm. The rest of the stuff is only in DB, so it's not a problem. Ah, hmm. Previous year assignment problems. At least that was what I was supposed to solve. Yes, it's not correct, but that is not my problem, no. I didn't even know that they are the same questions because they should alternate the questions uh, every 2 years or 3 years, like that. So, anyway, yeah, because you'll find these tutorial videos from 2 years ago also, because this will be repeated for some year. Yeah, maybe I'll just not give you the numbers, I'll give you the method and then you can plug it in from next question. I don't know why they have given. Do they give the same questions every year? Yeah, yeah. That's no video will be same every year because they will only record once. It's very expensive. No, they'll record the lecture videos once, but assignments will be changed so that it won't repeat to the next year or at least 1 or 2 years. It will be different. Then again, they'll use the same thing after 3 years or like, something like that. They give us permission on NPTEL to view the previous ones. I can't give it to you. Yeah, maybe the course TAs are not that active with the scores. Maybe they got confused. Was week one also the same? Yeah, fine. We'll go to question 5. Consider an indoor Wireless LAN with FC equals 900 megahertz, providing coverage in a circular area of radius 15 meters using omnidirectional antennas. Under the free space path loss model, what is the minimum transmit power required at the access point in order for all terminals within the cell to receive a minimum power of 10 nanowatts. Okay, they've given you FC. You can find lambda, C over FC. Then you know from class that P received is P transmitted by 4 pi d over lambda squared, which is PT by path loss. So PT is path loss into P received. In dB, PT is P received plus path loss. P received has been given minimum power of 10 nanowatts converted to dB. Path loss you can find from 4 pi d over lambda whole square. That's the path loss converted to dB. And that's it. That will give you the transmit power. If the questions are repeated, I won't give the solution, but at least the math you should be able to do. Then 6, consider a breakpoint path loss model with d break equals 100 meter and path loss exponent after d break is 4.2. A base station is set up considering The maximum path loss to be 120 dB. What would have been the range of the base station for a carrier frequency 1850 megahertz? Again, frequency is 1850, lambda is C over Fc. First you find lambda, then if d less than d break, you have some formula for path loss. If d greater than d break, you have some formula for path loss. I won't give you the formula so you can go and look at the lectures. Then what you do, first assume d less than d break. Find the path loss PL1. If sorry, find the distance, assuming path loss is PL1. Find d, assuming PL1 is 120 dB. So they have given the maximum path loss is 120 dB. If d turns out to be actually less than d break, then the calculated value is the actual value of d. If d turns out to be more than d break, our assumption must have been wrong. Then this PL2 is equal to 120 dB. Calculate d by substituting all the known values in the formula for PL2. That's how you solve the problem. At least you have to go back and look at the notes if you want to know what is PL1 and PL2. And you have to know what the model is. breakpoint model, and what is the formula for path loss in either of the cases. Then consider a GSM user operating in below 1 GHz frequency range that corresponds to ARFCN of 64. What is the center frequency of uplink and downlink? Now you have two separate bands, uplink and downlink. You go back to the lecture and see for GSM what is the uplink band and what is the downlink band. Say this is F1, F2, F3, F4. Then there is a guard band. I'll give you a guard band frequency, FG. You have to leave half of that on one side, FG by 2. Sorry. Then each channel has some frequency band that is allocated. So half of that is given as guard band on both sides. And then you have the channels, how large the channel is, that is F, write it in megahertz. Then, so this is divided into different channels, and then the center frequency for uplink will be your F1 plus the channel number ARFCN into the channel width, which is F. Similarly, center frequency for downlink will be F3 plus ARFCN into F. So it is your job now to go back to the lectures, find out at what frequency the uplink starts and ends, what frequency the downlink starts and ends, what is the width of each channel that is allocated, how much is the guard band, so that at least you know what are the typical values for a GSM operation. Next, which pair of multiple access scheme and duplexing type corresponds to a GSM system? So in the previous question, I showed you that the uplink and downlink for GSM has two bands, two separate bands, and from that you should be able to recognize what type of duplexing is required and what type of multiple access scheme is required. That is covered in lecture. So uh, we saw that a frame is divided into different time slots. Last week, Professor had shown an example. So what you can do is, if a single slot is being used by a user, then we can give one time slot for the uplink and a different time slot for the downlink. And what this means for the access, you figure it out yourself. Because here there's nothing I can really say the answer is just straightforward. If I tell it to you, you'll know. In a GSM system, which statement is correct about duplex filters? So again, recall from the previous problem that even though it's frequency division duplexing here, the uplink and downlink are actually happening in different time slots. So if they're happening in different time slots, do you need a duplex filter or do you not need a duplex filter? Will that change anything? And depending on that, you can choose your option. Find the overall noise figure of a four-stage cascaded amplifier. So if you have an amplifier like this with signal power Si, noise input power Ni, gain G, and some ambient noise is being added Na, the noise figure for this system F is SNR input divided by SNR output, which is Si over Ni divided by GSI is the output power, GNI plus Na. Then you can eliminate the GSI. You can, in this part, you can divide both the numerator and denominator by G. You get Ni plus Na over G. So effectively, what is happening here is uh, initially you had some noise when you pass it when you pass the signal and noise through an amplifier. Some other noise gets added to that noise, which is actually the ambient noise suppressed by a factor of G. Here again, you can remove the Ni from this part, from the denominator, take Ni common. You get Si over Ni divided by Si over Ni by 1 plus Na over Gni, which is nothing but 1 plus Na over Gni. That you can write Na is Gni into F minus 1. Okay, now I have given you the noise figure for a single stage amplifier. How to do it for a multi-stage amplifier? You can try to think of it yourself, or you can go back to the lecture and watch it. Professor had explained the derivation for a multi-stage cascaded amplifier. So essentially what happens is that the noise figure at each stage is suppressed by the gain of the previous stage. So it is very essential that you have a very good noise, very low noise figure for the first amplifier that you have, because the noise figure, the ambient noise that is added, gets suppressed by the gains of the previous stages as more and more stages are added. So the most important part, as far as the noise is concerned, is the first amplifier that you put in a cascade. That's the key takeaway from this question. 11. Which one of the following schemes enable all the users to use the entire bandwidth simultaneously? The TDMA, CDMA, or FDMA? Now, FDMA is straightforward. Each user is given a different frequency, so all the users are not accessing the entire bandwidth. That is very quite straightforward. TDMA is your bandwidth. TDMA, the time is divided into slots, and so in the first slot, one user will transmit. Second slot, another user will transmit. So in different time slots, different users are transmitting. But what does that mean in terms of bandwidth? That you think for yourself. If different users talk in different time slots, can they use the entire bandwidth simultaneously or can they not use it? Then finally, you have code division multiple access, in which users can transmit at the same time using the same frequency, but different spreading codes are used. Using different spreading codes, does it mean that you can use the entire bandwidth, or are there any restrictions? You think about that. Obviously, FDMA is you can't use the entire bandwidth, so that's already ruled out. These two things, you think of which one of these allows you to use the entire bandwidth, or do they not both allow you to use the entire bandwidth? Why is the shape of a cell not circular? Okay, suppose I am using circular cells. Let's say this is one cell. Where should the next cell be? Let's say this is radius r. If I should I put the cells like this? Is this a good way of splitting your area into cells, or should I separate the cells like this? Are we losing anything if we do this? And what if we use a hexagonal cell? Just by looking at the diagrams, you should be able to tell what's the difference between a hexagonal splitting, hexagonal cells, and circular cells. This has some disadvantage. This one has some other type of disadvantage. And you look at the options and see which disadvantage is present in circular cells. Just from the diagram, you'll know. Which of the following can be considered as the advantage of using frequency reuse? The same spectrum can be allocated to the other cells. Only a limited spectrum is required. Increase capacity, the all of the above. So think of it this way. If you have just one base station which has enough power to transmit to the entire area, but you have a limited frequency spectrum available to you, and you want to separate the users in frequency. That is, you want to give different frequency slots to different users. You're doing frequency division. So you have to split the bandwidth into channels. Each channel, let's say, has some frequency f. What is the number of channels you can have? It's the bandwidth divided by the frequency of one channel. Instead of doing this, if we had split this into cells and cell clusters, I won't write that well. where there are base stations in each cell. One good thing would be that each base station can transmit with lesser power. One bad thing is that there are more number of base stations. And suppose these guys are using the same frequency. So in this case, in the first case, how many users can the base station serve at a time? So number of users served at a time is equal to the number of channels. Here, how many users can you serve at a time? Assuming that users in one cell do not interfere with other cells using the same frequency. So you find out how many users can you serve at once. That will tell you whether channel reuse is better or not. If you can serve more users, that means that's an advantage. And for the second point also, it's the same thing. Suppose you have a certain number of users that will call at a time with a high probability, and you don't want to say no. You can't say if the service provider, who is there BSNL or Airtel, whoever it is, you can't just say no. I won't give you. I won't let you call. You already paid, so you should be able to call at any time. But the problem is only a limited amount of spectrum is present. So how does that play out? By using the same frequency, you can use lesser amount of spectrum. Is that a good thing or a bad thing? And then what does uh, it mean to have? How does this affect the capacity? Does it increase capacity if you have more, if you have cell splitting, or does it decrease capacity? So most of these things are discussed in the lecture. You go back to the lecture, watch it, and choose the options correctly. Then from 14 to 17, you have some information that is used in all the questions. Consider a cellular network built with 4 cell clusters, radius of each hexagonal cell 1.2 kilometers, base stations with omnidirectional antenna, transmitting at 2.4 gigahertz within a cluster. Assume no interference. So adjacent cell interference is not there, only co-channel interference. Base station transmit power is 1 kilowatts. D break is 1 kilometers. Path loss exponent is 3.8. That's the information for 14 to 17. 14, what is the co-channel reuse ratio of the network? So D over R is proportional to square root of n. D over R is k times square root of n. What is the value of k? What is the value of k? You go back and check in the lecture videos or lecture notes. N is the number of cells per cluster, which is 4 in this case. So D over R is 2 times k. Find out the value of k. What the lecture video? Then question 15 says, in the worst case, huh? Yes, yes. Your audio is cutting off. Can you ask your question again? Okay, I'll show for the next question. Huh? We need that for next question. 15 in the worst case SIR due to only tier 1 interference. What is the distance between the user and the strongest interfering base station? Now it's a hexagonal cell network. So the cells are still they're still hexagonal only, but the way we form the clusters is different. That's all. So the hexagonal structure would be like this. We can keep going as much as we want to cover the entire area. This doesn't change with the value of n. Of course, all the cells should be of the same size. I'm not very good at drawing. Okay, now you start at some point. There are different ways you can choose any four adjacent cells, and that will be a cluster of four. Only thing is the orientation will be a bit different. You can choose any four adjacent cells. You can choose something like this, and that's valid. You can choose something like this, no problem. Here we'll choose this. Then what will happen? You just have to make sure that this figure, if you repeat it, you'll cover all the you'll cover the area properly without gaps. So the next group of four will be here. The another group of four is That's an adjacent cluster. Another cluster is this one. You can form clusters in different ways also. This is not, this orientation is not standard. You just have to have four adjacent cells in your cluster. Now, at the end of the day, you will end up with six clusters which are adjacent to any one particular cluster. With six, how many is it there? It's yeah. Now, which are the co-channel cells? This is 0. Let's label it as 0. This is 1. So in each of the clusters, the co-channel will be in the same position as your channel is in the cluster that you have picked. So in this cluster, if you label this as 0, 1, 2, 3, then let me put it this way. If you label this as 0, 1, 2, 3, then here also 0, 1, 2, 3. Here also it's 0, 1, 2, 3. 0, 1, 2, 3. So it will be the same labeling scheme in all the clusters. And what I mean by these labels is that a cell named 0 in one cluster, the cell named 0 in the other cluster both use the same frequency. So these are the co-channels that are reusing the same frequency. So if that is how the labeling is done, if I call this cell C0, then its co-channel is this particular cell, call it C1, and this cell C2, this cell C3, this is C4. Did I make a mistake somewhere? I think I made a mistake in these parts in forming the clusters. Let me erase them and do them again. this was the one of the adjacent clusters, and this is another adjacent cluster. Okay, so I had made a mistake previously in drawing the adjacent clusters. Now it's correct. This will be C5, this will be C6. Okay, so you have six co-channels here also. Now you have to find the distance between the user and the strongest interfering base station in the worst case scenario. In the worst case scenario, the user is at the farthest distance from the base station in its own cell. So the user will be, if we consider cell C0, user will be somewhere here. Then the uh, so here you have uh, you started out with this cell and you got six clusters surrounding it, right? Now you start out with the co-channel. There will be six clusters surrounding that co-channel also. It will be it will have a similar pattern. And similar to how this C0 and C3 are using the same frequency, if you now shift your perspective from C0 to C3 and take this as the central cluster, there will be six clusters surrounding it, and there will be some other C7 here that will be using the same frequency as C3, but C3 is using the same frequency as C0. So now that means C7 is using the same frequency as C0. So C7 can also interfere with C0, but that is at double the distance from C3. So that is a tier 2 interferer. The, the set of closest co-channels are tier 1 interferers. Here we are considering only the six clusters surrounding adjacent to it. There might be other clusters which are not adjacent to it. So this, whatever cluster will be here for cluster of 4, that is not adjacent to this cluster that we are considering now. Okay. I don't think they will ask you to calculate SIR and all for tier 2 interferers because they are quite far away and the complicate even just from calculation point of view, doing it by hand will be harder. If they ask, then you will have to again whatever you did for C0, repeat that for C3. Then you will get co-channels for C3, and those co-channels will also be co-channels for C0, and they will be tier 2 interferers. Now, in the worst case, you have the user the furthest distance from his own base station, which is at the center here. And when he is this far away, among the tier 1 interferers, which one causes the highest interference? That will be the uh, base station which is closest to the user. We call user U. So you have to calculate the distance from here to the user. Then calculate the distance. Calculate this distance. Just from inspection, you can see that this guy C3 is farther away from you compared to C1 or C2. Similarly, C4, you don't really have to bother. C5 and C2, you can see they're kind of at the same distance, and C1 and C6 are also at the same distance. Just from inspection, you can see C1 and C6 are closest. But if you're not sure, you can find the distances and calculate it. And you can see that from symmetry, C1 and C6 are at the same distance from P, so you can find any one of the distances. Now, I have not drawn the diagram very carefully, so it is not very clear how to calculate what is the distance between C0 and C1. But if you draw this portion separately, if you had drawn it properly, it would be something like this. So you can find out the distance of this point here by writing this point as the origin. This is for a hexagon, the side is equal to the radius. So this is R, this is R, this is also R. So it is at the point 3R. So the x distance, this distance is 3R. Now here this distance is root 3 R over 2. So each of these is root 3 R over 2. There are four of those. Uh, because this is an equilateral triangle and that is a bisector. And so this is R by 2 and this is R. So it's square root of R square minus R square by 4. So it's 3R square over 4, which is root 3R over 2. Just give me a minute. Okay. All right. We don't need the hypotenuse. I'm trying to write it in the. Trying to write the coordinates of that point. We don't need this part. So trying to write the xy coordinate of this point, which is C1. This point is C0. So x is 3r. This is no, it won't be 2r. It's from here. It's this distance. That's the y distance. So this is it's 2d. See, in this hexagon, this distance is r. This length is also r. This distance is r. This is actually what is called as d, and d is root 3r over 2. Or is it root 3r? Uh, it's root 3r over 2. I did it just yeah. So that means it's this distance, y distance is 2d. So this is actually 2 times root 3r over 2, which is root 3r. So the point C0, if you take that as the origin 0, 0, the point C1 is at 3r comma root 3r. And your user U is actually at, he is at r comma 0. So the distance between U and C1. Now I am taking a rectangular coordinate system, so um, distance is just 3r minus r whole square plus root 3r minus 0 whole square, which is 7r square, root 7r. And this is the closest distance. Okay. Yes, if the base station is closer, its interference is stronger. Because you see, in the power transmitted and power received, you had the free space path loss. Power received was P transmitted divided by 4 pi d over lambda square, which is inversely proportional to d square. So it gets attenuated with the distance. That's why it has strongest interfering base station, which is the closest base station. So uh, closest base station is C1. They're asking the distance between the user and the strongest interferer, which is the distance between the user and C1. Then you have to calculate what is the worst case SIR for the user due to only tier 1 interferers. that you can calculate as, again, this is the worst case. So the user in the position I have shown, user is here. Now you have to find the distance between the user and all the other transmitters. That I will leave it to you. Then you will get SIR is P received due to C0 divided by P received due to co-channel I, and there are 6 co-channels. Now, since the distance will be greater than d break for all of them, because the cell radius is 1.2 kilometers and d break is 1 kilometer. So all the base stations are at a distance greater than d break. So the transmitted power is, or the power received by the user, PRCI, is P transmitted by the base station divided by 4 pi d break 4 lambda whole square into d duci. That is the distance between u and cochannel ci divided by d break whole square. Now you have to find the distance duci for each of the cochannels and substitute in the formula. You can make it a bit simpler because we transmitted 4 pi d break over lambda whole square and 1 over d break whole square are same for all the base stations. So in the end, what is important is only what is left if you cancel the numerator and denominator is only the distance duci by duc0 to the power minus n, where minus n is the path loss. Oops, this was path loss. You do this, substitute, find duci for each of the co-channels and plug it in, and you'll get the answer. Question 70 says if the noise figure and thermal noise floor of the user's receiver are 10 dB and minus 100 dBm, what is the SINR for the scenario in question 16? That means the same setting, except now your receiver has some noise floor, thermal noise, and also its own degradation noise figure. This is simply just SNR, just simply again it's P transmitted, which is the it's P received by the user from the base station in its own cell divided by the noise power plus again the interference. The formula for all the other things remains the same. And as you know, Pn is 10 log KTB plus noise figure, 10 log F. That's thermal noise floor. So this is in dBm, right? What unit is it in? It's dBm plus noise figure in dB, and that'll give you Pn in dBm. So if you add a quantity in dBm with some some dB, then the result is also in dBm. So you get that, then you substitute again. You'll find out an interesting thing, which is that the SIR and SINR in question 16 and 17 are almost the same. So that is, so the, yes, you can. Can't add dBm and dBw because there are different units. dB is just a multiplication factor, so you can add. You try to find the things in normal units without dB and figure out the answer. You will find out that it's actually correct. That you can add. So dB is not a unit. dB is just a multiplication factor. So dBm is a unit. It means some power in some milliwatts. So if you had 10 milliwatts and you said my amplifier will multiply it by 10, then you have 100 milliwatts at the end. So that multiplication factor of 10, if you express in dB, and the milliwatt, if you express in dBm, it just means you are multiplying by 10, right? Even if it's in dB. So you can directly add. Okay. You figure out the answer to both these questions, 16 and 17, you'll find out that they're not that different. So, as you saw in the lecture, you have noise floor, then margin and all. Here, this is distance, this is received power, and as the distance increases, received power decreases. So, usually you have to, this is the maximum distance you can transmit to. But if you have another interfering base station that's like this, then depending on how much SINR you need, this will be your SINR. So the actual distance you can transmit to depends mostly just on the interferer instead of the noise, thermal noise. Okay. Hopefully you will be able to solve your assignment questions with these as your guidelines. I've given you most of the methods and some cases formulas also. Some cases you have to go back and find out the formula from the lecture. Other cases you just have to plug in the numbers. All right. Good luck with your second assignment. I'll see you next week. Next week I'll try to find some other year's assignment or some other problems so that it's not a repetition of this year's assignment and it's not cheating. All right. Good night.